Hey there, fellow wackadoos. Hello again. Welcome back to Dr. Doodle's QBasic Asylum. Looks like we're crawling up on episode 31. Scrawl out a message in QBasic. Yeah, now, I don't know if you can see, but well, right about there is a puncture wound from an IV I got on Cinco de Mayo when the beautiful young Mrs. Doodle and I, we scheduled his and hers colonoscopies because we're romantical like that. And once again, the doctor is certified that I am, indeed, the perfect asshole. In fact, he even signed an affidavit stating that my head is not, in fact, up there, despite constant claims by Mrs. Doodle. But anyway, enough of that tomfoolery. Yeah, so, SCRAWL, we're going to take a look at that right here. Right here. Alrighty, so, well, here we have QBA31.base. It's called SCRAWL. Of course, as always, copyleft 2025 by Dr. Doodle. And, well, we'll just run this here, see what this thing does first. And, boop, there we go. So there it is. Now, we got the SCRAWL help screen comes up here. Basically, it's a paint. Well, and let me just click this here. What you do, you just click and draw. Scrawl whatever you want to do there. And probably too dark. Let's try this. They're too light to see. There, that's better contrast. Good, good, yeah. Well, the idea is you can select different color, what have you, and all this nonsense. Basically, it wants to be a paint program, but it's not quite because, well, it has no copy and paste, no functions for drawing circles, boxes, what have you. But basically, you can just scrawl screen all over the screen, which is why I call it SCRAWL. So, clear the screen here, and let's see what we got. Well, we've got, starting the top left, SCRAWL QBasic print program by Dr. Doodle. Here's the cursor state, which we'll talk about that. The horizontal and vertical coordinates. Now these colors here, this is your palette. You can select if I want to draw in green, for example. There's green, or click here for brown. Brown, how about the aqua? That's cool, yeah. And now these should be pretty evident here. Clear, clears the screen. Help brings up this help screen here, as it says. SCRAWL help screen. To draw, we just click on left mouse and drag. Clear screen, left click on clear right there. Select the foreground color, left click on the color bar. Background color, right click on the color bar. View help, this screen, click on help right there. To quit, click on quit. Hey, this is pretty simple, guys. I can't make it easier than that. Now, save screen to file. Left click on save and enter file name. And then to open a save file, left click on open, enter the file name, press any key or mouse button to continue. So that's what it is. That's what it does. Let's, how about we scroll out a message here. How about Dr. Doodle, that's me, is awesome. Because let's face it, I'm awesome. You know it, I know it, we all know it. Dr. Doodle is awesome. And we save this as Dr. Doodle.dat. Boom, there we go. So we're saving the file. Takes a bit because it has to read all these pixels here. One by one by one. Alright, so we've saved this here. Dr. Doodle is awesome. And so now let's clear the screen. Reopen this. Hang on a second. Dr. Doodle is a turkey. What? I don't need your opinion. Listen, I want your opinion. I'll give it to you. What's going on here? Alright, I gotta come clean, just a little clever editing here. Look here, I say this is file DDT, Dr. Doodle Turkey. Let's open DDA.dat, boom. There's our original file. I actually just saved this much of it and then filled in the rest later. But anyway, enough tomfoolery. Let's take a look at this pig and see how it works. We just click on quit, boop, and we're back to the main screen here. So again, from the start, QBA31.base called SCRAWL, copyleft 2025 by Dr. Doodle. First we initialize the program. Now this time, instead of integer, we're define long A through Z. Instead of integer, they're long integers. Reason, we'll see what that's all about later, but we're going to be using numbers that are too big for just integers, so we're calling them long integers. Now we declare the sub mouse func. Again, we've seen that dozens of times. We go subdue screen. C colors 14. That's the foreground color. Background colors 9, and that's, what is that? Reddish, I guess. I don't know. But we do a line here that fills the whole screen. Cursor option is 0, and mouse equals 1. Go sub help. We'll look at the cursor option in a moment. So here we are, the main program. We got the program loop here. Do loop, and then until in key equals character 27. That's the escape key. Then quit. Mouse 2, clear screen, and system. So we go back to the top here, mouse 3, of course we want to read the mouse coordinates, what buttons are pressed. Here we print locate 224, print the horizontal, and then the vertical. Select case B, that's of course the buttons, the mouse buttons. If we press none, 0, then ready equals 0, mouse equals 1. So turn the mouse cursor on. Case 1, if we've hit the left button, then select case V. Now for 0 to 14, so from 0 to 14 pixels down, we're up in this top region above the drawing section there, so drawing field. So now we can select H horizontal, and if it's from 455 to 519, we'll go sub to save file, case 520 to 565, then it goes up open file. That's the save and open the file. Now case is greater than 570, sound equals 880 and 1.5. In other words, if we're over here where there's nothing there, it just beeps. Basically you're not clicking on a button, it's just empty space, so it beeps and returns. Now case 15 to 33, that's the second row down here. Again, we look at the horizontal. If case is less than 99, cursor, that's over here, cursor option equals 1 minus cursor option. So in other words, if the cursor option happens to be 1, then we subtract, cursor option is set to 1 minus 1. So now it's 0. Now again, cursor option is equal to 1 minus, in this case, 0, so it goes back to 1. In other words, we've seen toggles before. Every time it hits this line, it just toggles cursor option from 1 to 0, and we'll take a look at that in a moment. Mouse 2, we hide the mouse. Locate in 2 and 9. If cursor option equals 1, then print hide, else print stay. So do mouse 3, loop while B equals 1, mouse equals 1. Now, in fact, I should probably show you the difference here between hide and stay. We'll run this. Boom. So we're ready to draw something. The cursor is now stay. So as you see, while I'm drawing, the cursor is there. But if I go up here, it can kind of get in the way and be a little confusing. So we can click here and hide. Now when I draw something, the cursor disappears. It's not in the way if I try and draw it up and down. I can see if I'm right in little tight spaces like that, just makes it a little clearer. Now if I come back up here and click here again, now it stays, and when I draw something, the cursor stays there. So it's just easier to see. That's whatever you prefer. If you like to see the cursor or not, just click cursor or stay. Alright, quit. Now back here, yeah, if cursor equals 1, then print hide, else print stay. Now we do mouse 3 loop while B equals 1, mouse 1. Okay, and then turn the mouse on after we finish drawing. Now, case 310 to 432. What this is if we're hovering over the palette there, the color palette, that we're selecting what color we want. And if we're pressing button 1, then C equals H divided by 8 minus 38. What? Well, it sets the foreground color to H divided by 8 so that it tracks properly in this particular screen mode. Now we subtract 38 so that it returns the right numbers from 0 to 16, the colors you see up there. Alright, well, see, I'm not satisfied with that explanation, so hopefully this will clear things up a bit. Now the reason I'm dividing H, the horizontal, by 8 is because each of these little color boxes here is 8 pixels wide. See, now there's different columns, whatever columns here. So like for example, the first 7 columns here, 0 to 7 will return a 0. 8 to 15 will be 1. 16 to 23 will be 2, etc. By the time you get up to here, we're up to about 38. That's because 310 divided by 8 is 38. So we subtract the 38 to give us back to 1, then 2, 3, 4. In other words, each of these bars is 8 pixels wide, so we have to divide by 8. But this would give this a value of 38, and we want to get down to 1. That should be 2, 3, 4, so we just subtract 38. Hopefully that clears that up. Baby, you helping Daddy? Oh, helping Daddy with the latest video? That's my little girl. Oh, gypsy girl. Now don't sit on the pewter. I might need that later. Silly girl. Alright, we'll get you some treatsies. Hang on. Now, case 454 to 519, mouse 2, it shuts off the mouse, and then line, okay, this draws the full screen in reddish color, and then yellow, the box around it. In other words, we're just erasing the screen or clearing it by printing a box over whatever the background color happens to be. It prints a filled box of that color, and then the 14B, that's the yellow border around. Then mouse 1 turns that back on. And case 520 to 565, we go sub help. We'll see that in a moment. If case is greater than 570, then go sub quit and select H. Now, case equals greater than 33. In this case, we're down below into the drawing field now. And we go sub draw something and select V. Case 2, if V is less than 31 and H is greater than 31, H is less than 43, and then go sub background. In other words, again, we're currently hovering over the color palette there, but instead of button 1, we're pressing button 2. So we're selecting, instead of the front foreground color, we're selecting the background color. Same idea. Case 3, and now we mouse 2, clear screen and system. So if we hit both buttons, then it just quits the program. And select B. And we loop until in key character 27 until it puts escape, and then also quit mouse 2 to turn off the mouse, clear the screen and system and the program, and select B. Now loop until in key equals character 27 or escape. So you can hit escape, you can hit both buttons or click on the quit button. There's a lot of ways to get out of here, but that's the main program. So let's take a look at the sub routines here. They do the bulk of the work, and again, this is where the nitty gets gritty. So we do screen. This is draws the screen, of course. Sets the screen to graphics mode 12, which is 640 by 480 pixels and 16 colors. Line 0 to 640, 34, that just draws a black square up top here where all the text and such goes. Now view screen is set to that. Line, yeah, there's the yellow border around there, color 13. Now we locate and print SCRAWL, QBasic print program by Dr. Doodle, print save, open, cursor hide. You've seen all this. It's just basically building up the screen as we see it. So help, this just prints the help screen that you saw earlier. Mouse 2 to turn off the mouse cursor. Now if the background color is greater than 8, that means we're clicking on one of the lighter colors, then shadow equals background color minus 8. And what this does is if say you're on light blue, we subtract the 8, that makes the shadow a dark blue. If it's on light green, then that makes the background, the shadow, dark green. Else, if it's a dark color to begin with, the shadow is just 0 because there's nothing darker than that. I hope that makes sense, but you can play with the colors and you'll see what I mean. Now we draw the line, and there's the shadow, the box fill, a line for the screen itself, and we print all the text that you saw here, left click, etc. Basically just print the little hint box that you saw up on screen. Nothing special there. Draw something, as the name implies, it's where we actually draw something. And if ready is equals 0, then old H is equal to H, old V equals V, ready equals 1. All this does is it finds our initial starting coordinate. Now we turn off the mouse and read the mouse, see where it is. If V is greater than 33, we're now in the drawing area. So if at this point we can start drawing line from old H, old V to H and V in whatever foreground color. Old H equals H and old V equals V to update these. So each time through the loop, we find the latest coordinate and draw it. And if cursor option equals 1, then mouse equals 1. Why do we need this ready? Well, hang on a second. I'll just run this out and we'll see what this does. So run. Okay, now we're ready to draw something. Let's just maybe start here. Oh, wait, what's this line all about? Well, it's because we have not yet got the starting coordinates, so it just starts at 0, 0. And we end up with that line. Let's clear this again. And maybe we want to start drawing over here, but it's where the last point was. Anyway, quit. We just need to find the initial H and V coordinates before we start drawing. I don't know if I explained that well enough, but you'll mess with it and you should see what happens. Now, Background color should be pretty simple enough. If we hit the right button, we call the background color. Background color is equals to H divided by 8 minus 38. And again, in order to report one color from 0 to 16, mouse 2 to turn it off. We'd line here, whatever background color we selected, we do a filled box of that color, and then 14 around the border there, and return. Now save file. Okay. Save file is a bit tricky. I don't know if you happen to see episode 17, I guess it was. It was called QBasic Mish-A-Mash. I mentioned something called delta tracking, which is a data compression scheme I came up with. This actually uses the delta tracking scheme in order to compress data. Now, hold on just a second. I'll insert a clip from episode 17 that explains it a little better, and then we'll come back to this. Now it's time to talk about graphics, specifically bitmaps. Now here we see this little smiley face here. This is our little smiley face. Now if you look, these squares are, each one of these squares represents one pixel. So there's a pixel, 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 etc., etc. We got our, there's white, there's yellow, blue, and red. So 4 different colors. Here's our pixel. We want to save this to disk. Now what do we need to do? Well, we need to know each pixel. Where is it? What color is it? And we need to save this information to disk. How do we do this? Let's take a look at this. Hang on one second. All right, now here we have the same bitmap, of course, but now if you notice these numbers here, I don't know if you can read them or not, but we've got, this is numbered now, each pixel, that's row 1, column 1, and then color 1. It doesn't match up with the color for QBasic, but it doesn't matter. This is just the first color we come across, so we call it 1. All right, so this pixel, row 1, column 1, color 1. This is row 1, column 2, color 1 again. Row 1, column 3, color 1, row, etc., etc. So you get the idea. So how would we save this to disk? Well, we need to write down each of these pieces of information. We got 1, comma 1, comma 1, then comma 1, comma 2, comma 1, comma 1, comma 3, comma 1. We got 1, 2, 3 pieces of information for each pixel. So 10 by 10, that's 100 pixels times 3 pieces of information. That's 300 bytes of information just for this one little bitmap here. And that's 10 by 10 pixels. So if you can imagine a full screen, that would be too much information. So how can we decrease that? Well, I don't know about you, but I don't count 1, 1, 1, 2, 1, 3, 1, 4. I just count 1, 2, 3, 4. I don't need to know the row and columns. I just need to know the number of the pixel. So can't we do the same thing with our bitmap? Well, turns out we can. Hang on one second. All right, so here again, same bitmap. But now if you notice, instead of row 1, column 1, it's just 1. Row 1, column 1, there's just pixel 2, pixel 3, pixel 4, etc. 1 up to 10, 11, 12, 13. You get the idea. So now we're doing the same thing. We're just going pixel by pixel, but instead of recording row 1, column 1, color 1, we're just doing pixel number 1 and color 1, pixel number 2 and color 2, pixel number 3, all the way down across. So now, again, the same 100 pixels, but now instead of 3 pieces, we got 2 pieces of information per pixel. Again, simple math, that's 200 bytes of information for this little image here. Now, so we went from 300 down to 200. Pretty good. It's not bad. But you know, we could do even better than that. Hang on one second. All right, again, we're looking at the same bitmap, but if you notice, only one number in each pixel here. Why is that? Well, again, with data compression, the idea is to get rid of redundancy. And what are we doing when we count up? We're just adding 1, adding 1, adding 1. So all we really need to do is just have the program have a counter in there. So we know that we're looking at pixel 1. The next time we add 1, that's pixel 2. We add 1, that's pixel 3. So we don't even need to record the pixel number. All we need is the color for that particular pixel. So we start up, we'll have the program will draw out 10 pixels, then drop down 10 more, drop down 10 more. So we just, that'll be pixel color 1, color 1, color 1, all the way across until it gets to the next row. 1, 1, 1. Oh, here we got color 2, color 2, color 2. So from 3 pieces of information down to 2, now 1 piece of information for each pixel. Again, 100 pixels, 100 bytes. So we've gone from 300, 200 down to 100. Again, pretty good savings. I think just for representing the data in a more efficient way. But we can do better still. Check this out. All right, now this time, if you notice, some of these pixels have no numbers at all in there. Why is that? Well, as before, we know that we're counting up, so we don't need the pixel number, just the color. But really don't even need the color at all, because look at this. That's 1. that's still color 1, that's color 1. So if it's the same thing, we can just ignore it. We can just have a counter on there and know that this is number whatever. Now, what we can do is we'll look at our first pixel and see what color it is. In this case, it's 1. Now, we check the next pixel. It's no difference, so ignore it. Again, no difference, ignore it. No difference, ignore it. No difference. Go all the way through the first 10 and then down to the second row here. Yeah, second row. Again, ignore. Oh, wait a second. Now we got something different. We have a different color. So what we do is we check, what's the number of this pixel here? 10 plus 4, that's number 14, and it's now color number 2 because it's the second color we've come across. So now what we would do in our file, we would put 1 in the bitnet map file. We'd just put 1. Ignore. Oh, now we got a change here. So we put in a 14 and then a 2. That's 3 pieces of information. But these again are same because the 2 is now the default color, so ignore. Oh, we're back to white again, so that's the 18, pixel number 18, and color 1. So we got 1, 2, 3, 4, 5 pieces of information. And we go along, this is a technique that I came up with, which I call delta tracking, because we're just looking for change. We don't care about anything about it. Something changes now. Oh, wait a minute. We got to figure out what's changed where and to what color. It's really all we need to track. Now, I'm sure didn't invent this. I'm sure someone else came up with this idea and scrapped it for a better one. But it's related to something called run length encoding, which is a more sophisticated technique. But again, if you look here, we just write 1. That's our color, or in whatever language you happen to have, whatever color corresponds to that color. But this is our first color, so 1. Ignore, all the way through here to, oh, there's a change. So we write down the number of the pixel and then the color. Same thing, number of the pixel, the color. So we just got 1, 2, 3, 4, 5. You go through here. I checked it out earlier. That's 61 bytes. So again, from 300 down to 200, 100 to just 61 bytes. Now this is actual data compression because what it is, we've actually encoded this information. It's not just more efficient. We've changed the way that we write down the information. So this is 61 bytes of information for this one little image, and we save that to disk. Now, when we want to view it again, we can write the program that knows how to interpret this. So it says, oh, okay, well, there's my default color. It's 1. I just keep writing pixel until I see something different, and then it changes. We can get this image back exactly as it was, the full, 300 pieces of information, just boiled down to 61. So that's data compression, at least in graphics anyway. And of course, you've got different techniques for audio, for video. Those I won't go into because they're much more complex. But I think you've got the idea here. The basic idea is just to get rid of redundancy, get rid of waste and slack, like with the archives, all the empty space, get rid of it. Okay, well, hopefully that made some sense to you. But so here we are in the save file subroutine. And first, with mouse 2 turns off the mouse cursor so we can do our graphics. Set the color to 14, which is yellow. Now we locate 160 up here in the top right. We input file name, and the file, we save that to a variable called file name. Next, we clear out the space below it, and we print saving file name. We just types out the name that you just entered there, so you see you're saving whatever file name. Now we open file name for output as 1. Color equals 0, locus equals 0, and for Y equals 34 to 478, so from 34 to 478 down. From X is 1 to 637, 1 to 637. And now we set locus to 1 minus 34, because if you notice we're starting here at 34, but we want to just start calling it 1. Even though there's space up here, we're start numbering from here. So Y minus 34 times 637 plus X. What? Well, assume we're on row 34. Well, Y minus 34, that makes it 0, times 637 is 0, plus X, which happens to be 1. That's now cursor number pixel number 1. If we move over to 100, for X is 100, for example, Y minus 34 is still 0, times 637, that's 0. Plus 100, so that would be pixel 100, and as we go down the Y, we divide by 637, and then we add the cursor. So basically each time you go down a row, it adds 637. Then we just add whatever column it is to get the number of the pixel, pixel 1, 2, 3, etc. Once we know the number of the pixel, if point x, y is not same as the color, then color equals point x, y, and write one locus color. Huh? Well, if you remember from delta tracking, we don't care. Once we get the pixel color, we can just ignore anything that doesn't change. So if point x and y is not color, that means it doesn't match. There's a change. Then color is now set to this particular point, and we write that information with the locus and color. So in other words, whatever pixel number we're at the present, it writes that and then the new color to the file. And if, and we just loop through the X and Y's. Once we're done scanning the whole screen, we close one, we locate 56, 1, 56, and 2, 56, print. We just clear that section out where it says saving, and go subdue screen. It reprints the screen. Mouse 1 turns the mouse cursor on, and I don't know why we're turning it on twice, but now we return. Let me see if I can clear this up just a little bit. Again, according to the delta tracking algorithm, we just ignore anything unless there's a change. So we start scanning from 34 to 478 from this point down, and then from 1 to 637 all the way across the screen. Locus is equals to y minus 34, because we're not starting here, we're starting at 34 times 637 plus x, which is the column. So let's say, for example, the mouse happens to be at row 34. Well, 34 minus 34 is 0, times 637 is 0, plus x. So there's no rows at the moment, and it's just whatever the column happens to be. Now, let's say we'll go down to the next row. Is now 1. 35 minus 34 is 1, times 637. So we add 637 plus the column. In other words, we're just calculating what pixel we happen to be on. Instead of x and y, it's just a single number pixel. And then we look at that point, and if it's not the same as the current color, then color equals point, and we write that information to the file. Locus, which is the current pixel, and then the color. And if. Now we cycle through the X and Y until we're done. Close one. We clear out this section up here, and then we go subdue screen. And then mouse turns the mouse cursor back on. Again, just go ahead and watch episode 17, and hopefully it'll make it a little bit clearer. But the idea is, all we're doing is we're scanning the draw section of the screen, and we come up with a pixel number 1, 2, 3, 4, whatever. If it's different from the previous pixel color, then we set the color to whatever it is now. We write that information to the file. The locus is the actual pixel we're at, and then the color is a new color. That's all we do to save the file. Now, to open file, okay, we go to mouse 2, turn off the mouse. Background color equals 0.236. That we get the background color that we've set there. The background color fill that clears out the screen. Color 14. Now we print up here input file instead of save files, input file name, and that's the file you want to load. We clear the space below it, and opening file, file name. At this point, we open file for input is 1. And we do until the end of file 1. That's EOF is end of file. We're just looping. We get input from 1, locus and color. That's the current pixel number we're talking about, and the color that changed it to. Now we calculate x and y. X is equal to locus. Now locus, this number could be 32,812, 62,000, whatever, some huge number. Well, we're doing mod 67. What is 637? What is mod 637? Mod, we haven't talked about this yet, but that returns the remainder of a division. So, for example, if our number happens to be, well, let's print this out here, and you'll see what I'm talking about. Print 637 mod 637, and we print this out. 637 divided by 637, that's just 1, no remainder. So when we do this, 0, no remainder. What if our number is 638? That's 1 too many. So 638 divided by 637 is 1. Goes in there once with a remainder of 1. Let's print this. Sure enough, remainder of 1. 639, it's 2 extra. 637 goes into 639 once with a remainder of 2. So we do mod 637, and there's our 2. Basically, all this is doing is showing us the remainder. Whatever the remainder is, because we're dividing by the width of the screen, so whatever the remainder happens to be, that's our column. That's our X position. That's how we calculate X. Now for Y, again, we're looking at locus, whatever that huge number happens to be, and we divide by 637 plus 34. Why are we adding 34? Because if you remember, where was it? Yeah, right here we're subtracting 34. Now we add it back in so it prints in the right place on screen. But if you notice here, we're dividing, but locus divided by that. Normally the division is a forward slash. Here we got a backslash. What's that? That's called integer division. And what that does, it returns the answer minus the remainder. I'll show you an example here. Print 11 divided by 2. What's this answer? Well, that's 5.5. So we return here. What do we get? Sure enough, 5.5. 5.5. But we don't want that 0.5, so we go integer division. Now 11 divided by 2. What does that give us? Just a 5. So integer division shows the answer minus the remainder. All we want is basically what row are we in. We don't care about, we can't be in row 4.5. There isn't row 4.5. It's either 4 or 5. So all we want is what row we're in. We don't need a remainder. That's why we use integer division. So to calculate Y, we take the locus, whatever pixel number we're on, integer division 637, and then we add 34, because if remember when we say that we subtracted 34, we need to add the 34 back in. Now we take a bit of a shortcut here. Let me load this and I'll show you here. Hold on, run. Okay, if you recall from the delta tracking portion, what it does, it goes through, and when it finds a change, it just draws a pixel, draws a pixel, draws a pixel, draws a pixel. Oh, there's a change. I need to draw a different color pixel, different color, different color, different color. Well, we don't need to do that. Watch this closely, and you'll see the lines, the yellow line there being drawn across. What's happening here? Let's say, for example, we're working on this line here. Instead of drawing a red pixel, red pixel, red pixel, red pixel, red pixel, it just starts here, draws a red line all the way across. Now it goes da 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 da. Oh, here's the next pixel I need to change. So it draws a yellow pixel all the way across. The very next pixel, oh, it's back to red. So we draw a red line all the way across. We keep going, keep going, keep going. And oh, here it's a yellow pixel, so we draw a yellow line all the way across, and finally another red line all the way across. So instead of drawing pixel, 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 we just draw 1, 2, 3, 4, 5 different lines. It just helps it to load more quickly. So it's a slick little shortcut that I came up with. Yeah, now we've calculated the X, we calculated the Y, we've drawn our line, and we can just loop through all the way top to bottom. Now we close file 1, we clear the section where we have the name up there, we go subdue screen, mouse 1 turns the cursor back on, and return. And I think that pretty much does it. I'm sure this is confusing as I am. I don't know how to explain it, but basically, yeah, we'll look through here again. And when we're saving our file, all we care about is change. Here, let's do this. And we get an input. We're asking the user, what file name do you want to save? We print here, saving file name. We open the file name for output as 1 to put the data in the file. Color is 0. Locus is equals 0. Now for Y equals 34 to 478. So we're not starting here at the top of the screen. That's all just text and crap. We start in the drawing section, 34 all the way down. And then for X we go from 1 to 637. Now we're just scanning each pixel, pixel by pixel by pixel. Now locus is equal to Y minus 34, because if you remember, we're not starting here, we're starting at 34. So we have to subtract that 34. Locus equals Y minus 34 times 637 plus X. What does that mean? Well, let's suppose, for example, we're in row 34. We're 34 down. 34 minus 34 is 0, times 637, that's 0, plus x. So whatever the x coordinate, the horizontal happens to be, that's the number of the pixel. Pixel 1, pixel 2, pixel 3, pixel 4. Let's say we're on row 35. Now 35 minus 34 is 1, so we're now one row down, one row of 637. So 1 times 637 is 637, plus the column. So we're one row down, we add 637, and then whatever the column happens to be. Hopefully that makes some sense. If the color at that point doesn't match the color we've already stored, then color equals whatever that color happens to be at that point. And we write that data, the current locus, the current pixel position, and the color. Now we just loop through X, loop through Y, all the way row by row by row by row until we're done. And then we close the file, clear the text area, go subdue screen, mouse 1, and return. And now for open file, it's kind of the same thing in reverse. We set the background color to 0.2, so when we clear the screen to load the file, whatever the background color happens to be, we just set background color to that. We draw a box filled in that background color. Now color 14, we locate input file name, and then we get our file name. We print opening file, the file name. Open the file name for input is 1. Now we loop until the end of the file. We just input the locus, the color. We calculate X and Y. We draw a line from X and Y all the way across the right hand side of the screen in whatever color we have, and we loop. Once we're done drawing the screen, we close file 1, locate 56 to just print spaces, go subdue screen to redraw the screen, turn on the mouse and return. Whew, I don't know about you, but I'm exhausted. But that's the gist of it. Basically, we're just selecting a background color, foreground color, and we're scrolling whatever across the screen, da-da-da-da-da. If we want to, we'll save the file for whatever. Just save it as X for now, and saving X. So we saved our file, and we'll clear the screen and make it, maybe the dark purple. Now we open X and enter. And you can see it's changing, it's drawing the line by line. What we're doing, we're just scanning the screen pixel by pixel. Wherever there's a change, we're at 1 pixel. What are we at here? And what color is it? We write that down. And there's another change. Okay, we write that down. There's another change, write that down. Once we got all that data, we go through to load it, and it just draws back and forth. Basically reads the data we already saved, draws it out on screen. So there you go. That's SCRAWL, and it's kind of worthless, but it does demonstrate the delta tracking, which is a form of data compression. Hopefully you'll enjoy it and learn something. Now let's take a look at, we got to do our Supeeriors, and let's see what we got this time. This will be fun. Hang on one second. Supeeriors! Alrighty, gang. Well, here we are at the YouTube channel of one Mr. Izzy Swan, a woodworker who is pretty famous on YouTube. He's got 954 subs and almost 500 videos. There he is, and this man is nothing short of a genius. Let's take a look at some of his videos. Well, speaking of genius workbench upgrades, no joiner needed. Build these jigs instead. Feels like cheating. Okay, this one, the sawmill retailers don't want you to see this DIY. Just amazing stuff. Sawmills, table saws, jigs and such like that. Yeah, there's a jig right there. No thanks, Festool. I'll keep my 1500. Don't buy a joiner. All the tips and tricks you can think. He's equal parts practical and just ludicrous. The things he comes up with. What's this one? Help me invent a woodworking tool. Yeah, and actually, I mean, like I say, he's almost 500 videos, and to save a little time, instead of searching through all these, I put some of them on my watch later list. Got to start with, where is it, the one, yeah, how to make gears with gear tape. This is kind of interesting. We won't watch the whole thing, but yeah, he's got what he calls gear tape, basically tape with teeth on it. You just wrap it around a round piece of wood, and there you got a gear. And that's just one example. Now look at this one here. This box is really a picnic table. Here we go. This box here. Look, check this out.
But at 80 pounds, it's a little heavy for my wife to get around or other family members. So I decided to.
That's the old design. He remade it. But look at that. An entire picnic table in a box like that. And this isn't even a new version he's got of. Oh, this one's fun. Here's a fun one. When's the last time you saw a pack of velociraptors running down the street after you? This is all made of wood and, of course, gears and such like that. But who makes this stuff? Well, Izzy Swan. Here's another fun one. Of course, they're all fun, but check this out. Tell me you wouldn't run ride that thing. Look how cool that is. That's all powered by a cordless drill, if you can believe that. Just, I mean, who wouldn't want something like this? I mean, Izzy's got another folding table, a washing machine. Where's this one here? Now check this one out.
You want to ride my dinosaur?
There you go. From jigs to tool reviews to woodworking techniques to full-size dinosaurs you can ride. Now, who else comes up with this stuff? Izzy is just, the man's a lunatic, but he's a genius. You got to check out his page if you're at all into woodworking. Hundreds and hundreds of videos. Lots of them are projects powered by an electric drill. Just a cordless electric drill does that. Who thinks of this stuff? You got to check out Izzy Swan. I've said it before. I'll say it again. You'll be entertained. You'll be educated. You'll be amazed. Must check it out. Thank you, Izzy, for your hard work and just insanity. But check out Izzy Swan. You will not be disappointed. I promise you. Go there, have a good time, and yeah, like that. Okay, so that's all we got for now. Yeah, but yeah, back to Izzy Swan. I mean, he's got hundreds and hundreds of videos you got to check out. So we'll head back to the video and wrap this up and get you on your way. Hang on one second.
Once I have that top 10.
Alright, gang, well, that should do it for this go-around. Hope you've enjoyed this madness I just dumped on you. Yeah, watch the video. And before I forget, thank you so much for watching, as always. You know, so many of you have been kind enough to subscribe, to comment, to like, whatever, but most especially shares. I truly appreciate all of that. But yeah, leave your comments and whatever you have down the thinger, download the stuff, play with it. You change it around, see what does what and why. Any questions? Yeah, right down there in that thing, and I'll happily respond to them as quickly as I can. But also, not just comments or questions, not just questions. Complaints? I want to hear complaints. Tell me what I'm not doing right. Tell what I'm doing right, please. I always love that. But if there's something you want to see I'm not covering, let me know. Other than that, I guess that's all I've got for now. Let's hope the next one's a little more sane. But till then, guys, hasta la pizza, baby.